is Moritz Hardt. Moritz Hardt has done foundational work in data analysis, privacy, machine learning, with emphasis on social aspects of these. Moritz is an old friend of the Institute. He's been participating in the programs in the very first year, the very first semester, and ever since.
All right, can folks hear me? Yeah, thanks so much, Prasad. It's a pleasure to speak here. Thanks everyone for staying to the end. It's fantastic to wrap up this very interesting workshop. Congratulations to the Simons leadership on the 10th year anniversary. I'll be talking about a line of research that actually started at the Simons Institute 9 years ago in one of the first programs in the Simons Institute. And that was the program on the theoretical foundations of big data analysis. It was very much about scaling up data analysis. There was something called exabyte scales roaming the earth back then, you know, if you've ever seen one. And, you know, it was an opportunity for theoreticians to learn about machine learning. Okay, so it was sort of, the goal was to take some theoreticians like myself at the time and teach them a little bit about what machine learning is about. And, you know, how we do statistics for data analysis. And so I came to machine learning as a bit of an outsider. And like many, I looked at this peculiar community and I noticed that it's structured and organized in a really interesting way. That's kind of unique actually to the field of machine learning. So there is on the one hand, like you know, a community of very skillful model builders that have given us many advances over the last years. You know, they have all sorts of techniques for fitting large models to data sets. And on the other hand, in this community, what seems to be very important are data sets that are used as benchmarks. Okay, and usually in science, we collect data to specifically refute or test a hypothesis, right? That's what people would do. But in machine learning, actually, you set aside data to use them as benchmarks. Okay, and then machine learning happens in some kind of iterative loop whereby the model builders propose a new model. Let's call that F. They run that against the benchmark data set of their choice. And they observe how well it's doing. Let's call that a loss. Okay, the loss of the model. So you observe how well your model is doing on the test set. Okay, and this could be something like CIFA or ImageNet, typical you know, image classification benchmarks. But at this point, there are really hundreds of benchmarks in machine learning, and it's really how this community is organized. Okay, so this seemed really interesting as a way of doing research. Okay, and so this is what I call the data sets as benchmarks paradigm. And it's really the pillar of machine learning research and practice. It's how we do this, right? It's how we you know, make progress in this area. And as such, we're putting a whole lot of pressure on this idea of data sets as benchmarks. And we're asking data sets to serve many vital roles in the community. First one is to sort of organize communities into things like vision and speech and so on. This is done often by what data sets you work on. Implicitly, these data sets sort out problem formulation, operationalize the problem formulation. So they kind of define what we're even trying to do. They're used to measure progress. They're also used to compare with humans to sort of give us a sense of how well we're doing relative to humans. That was what Sendel's talk was about. And that also shapes narratives about how far AI has come or not. And finally, they also interface between academia and industry. They give you sort of a code interface and a code contract of what a model for a certain type of problem has to do. Okay, but the fundamental question I want to ask in this talk is, does it work? Okay, does this iterative process of model building and testing lead to progress, lead to scientific progress, or does it somehow go off the tracks? Right? Does it somehow converge to like undesirable, you know, scientific outcomes? And what does it mean for this to work? Okay, and this is the kind of question we started asking 9 years ago. And in this talk, I'm going to give you some theory and empirical observations that have kind of come out over the last 9 years about what I think is sort of this emerging science of data sets as benchmarks and why I think there should be such a science too. Okay, so let's start with the basics. How many of you have seen the Holdout method at some point before? Okay, I think that's probably almost everyone. So this is kind of ostensibly, or at the outset, what benchmarks are based on. Okay, so in the Holdout method, you set aside a test set or holdout set of size n, drawn from some population, from some underlying distribution, let's say. And what you're going to do is you're going to evaluate things, you know, a loss function on average over this data set, and that's called the empirical risk. I'm going to write that R as of F. That's like the average loss of a model F on the data set, on the holdout data. And you use this empirical risk as an estimate of the risk, which is just the population expectation of the loss of the model on this underlying population P. Okay, so the empirical risk is something you have the data set on your hard disk, you can evaluate that, that's something you can compute. The population is not something you have, that's a theoretical construct. So you're trying to get at it by using the empirical risk. And what's typically done to argue that some such thing works is to look at the generalization gap, which is the difference between risk and empirical risk. It tells you how much the empirical risk underestimates the risk. And to say that that's small, okay, that hopefully, as we're evaluating our models, this generalization gap stays small. So we never really go astray in the sense that the loss that we look at on our holdout set is close to what it should be on the population, okay? And that's like one way of trying to argue that these things go well, okay? So if you do that for the holdout method, you can look at a textbook and you will see this kind of a textbook guaranteed for the holdout method. It's saying that if you fix K models independently of the data, and you evaluate them on the holdout method, then the worst generalization gap you're going to see over these K models is root log K over N, okay? Anybody have a proof idea? Chernow bounds, yeah, great. Chernow bounds, exactly. So you just do Höfting and union bound because you have IID data, these things concentrate. You take a union bound over K models, you get the root log K factor. And so this might seem great. You might say, okay, look, K could be exponentially large in N. We could be evaluating all these models on our data and we'd still be getting good answers. And I think, a lot of people looked at sort of this kind of textbook guarantee and we're like, yeah, that's not too bad. Okay, but there's a big catch. And the big catch is exactly that machine learning happens in a loop, okay? And the models are not fixed ahead of time, right? We iteratively build these models continually while like getting feedback from the holdout data. And this process, in a sense, adaptive, right? We're sort of tailoring the models that we built to previous evaluations of the test set, right? We're looking at like what we got, what the previous accuracy was on the test set, and then we're changing our model based on whether it improved or not, right? So we're incorporating feedback from previous evaluations of our models, which breaks the textbook guarantees of the holdout method, right? Because there's no longer independence. The functions you're evaluating depend on the data that you're evaluating them on, okay? And so this cycle is kind of the whole point of like how we do machine learning research. Like you can't specify all your models like back in 2010 and then collect all the data sets and see which one is best, right? That's not how we do it. This iterative process is exactly why we're doing well, right? So this issue of recognizing and addressing adaptivity, this was what started at the Institute 9 years ago. This was joint work with Cynthia Dwork, Vitaly Feldman, Tony Pitassi, Omar Reingold, and Aaron Roth. And I think Tony and Vitaly are in the audience maybe. And so we're partially inspired by this really interesting talk by Yoav Benjamini called Selective Inference and False Discovery Rate, which talked about an important problem of statistics. And it sort of drew our attention to issues of false discovery and how science goes wrong. And it was sort of on the heels of this whole debate about p-hacking and kind of the reliability crisis in the sciences. And we wanted to relate these sort of questions that were apparently very urgent, both to like the practice of machine learning and also like concepts from theoretical computer science that we were familiar with, okay? And so the first thing we noticed is that if you go to the adaptive world where models are chosen adaptively, the holdout method as it is can actually fail pretty badly, okay? So if you choose K models adaptively, the error that you're gonna get, or that in the worst case is order square root K over N. Okay, so contrast this with the log K dependence, you now get a linear dependence on K, meaning that after a linear number of queries in N, it's all over, right? This is pretty bad because the test set might have size 10,000. If you make just 100 evaluations, your error would be 10%. Okay, so this is too big, right? And so this is tight. You can find like a sequence of models which forces this error. Okay, so we first realized that this is kind of the guarantee is very weak in the adaptive setting. And so we're asking, can you do better? And in fact, you can do better, exploiting a connection between stability and generalization. What does stability mean? Algorithmic stability is a notion of an algorithm which says that if you change one data point, the learning algorithm, the output of the learning algorithm doesn't change much. So the picture is something like this. If you have an input sample S, and you change that to another input sample S prime by deleting or changing one data point, your output doesn't change much. Okay, it won't change much. And this is a form of robustness. And there's a set of theorems in machine learning that says stability implies generalization. Okay, so in other words, overfitting is not stable, right? Why? If you overfit to a sample, you must sort of have too much sensitivity in one of the data points, and as a result, you're not stable. Okay, so overfitting is not stable. This is a general principle, and it has nothing to do with adaptivity. It works in the non-adaptive case. It works, not necessarily in the adaptive case. But we sort of observed that this privacy guarantee, differential privacy, that have been studied a lot in the theory community, is sort of a strong algorithmic stability notion. It is kind of saying that if you change one data point, the output can only change so much in a certain sense. And we proved that differential privacy bounds the generalization gap, even if the analyst is adaptive. Okay, so even if the analyst chooses models adaptively, differential privacy guarantees that the generalization gap is small. And this is really specific to the composition properties of differential privacy. This is something where like other stability notions might fail. It uses the fact that differential privacy kind of composes when under like adaptive behavior. Okay, and so there's like a nice sort of connection between concepts from TCS and these issues that arise in machine learning. So what do we get out of this connection? If you fast forward a couple of years of research, eventually you get some bound like this. Okay, so there is a holdout mechanism based on differential privacy, so that for any k adaptively chosen models, you get error k to the 1/4 over root n. Okay, instead of this root k over n. But this is a lot of hard work. There was a beautiful work by Basili, Nissim, Smith, Stemmer, and Steinke and Oldman from 2016 that improved our earlier bounds. There's a lot of heavy machinery here. And unfortunately, you can show that this n squared that you get out of this is best possible. Okay, so this is giving you n squared model evaluations. And you can show that in the worst case, that's tight, assuming one-way functions exist. Okay, so there's also a hardness result which says that not exactly this rate is optimal. There could be another rate, but like more than n squared we can't do. Okay. And so it might seem this is where it ends. Okay, so that like we can go from n to n squared by using these tricks from differential privacy. But you might still say this doesn't really explain why machine learning works, because people have been using CIFAR and ImageNet for like more than a decade, and it's still going strong, and they made all these evaluations. And if this were the truth, then we'd be in trouble, I would argue. But there's actually, this is not where it stops, and you can actually go a lot further. And there's a more recent research that is more specific to machine learning, where you get much better bounds. Okay, and so this started with work with Avram Blum, who's maybe still in the audience. Yeah, hi Avram. And so it's what we call the Leaderboard Principle. And the best way to think about this is, let's think harder about the machine learning community, and let's postulate about the behavior of the machine learning community. And let's make the following postulate. Let's say that model builders are only impressed with significant improvements over the best previous model. Okay, so at any point in time, they care about the #1 model, whatever it is, the best current language model or the best current image classifier, and they try to improve upon that. Okay, this is an assumption about the inner workings of the community. It's sort of a sociological hypothesis, right? It's a postulate, right? And so let's assume this is true. Okay, that this community is very much obsessed with or being best or like improving upon the best current model. This leads to a notion of leaderboard error, where you have still the same adaptive loop, so full adaptivity, but your only goal is to maintain an estimate of the current best model. So at any point in time, you just want to know what is the best language model right now. I don't care about all possible models in the world. I just care about the best model. And I want to know which one is the best model and what is the loss of the current best model. Okay, so at any point t, you just want the best model. And if that's what you're trying to do, there's a very simple algorithm that works. And it goes like this. You just check if at any point in time when somebody gives you a model, you just check if that model beats the previous best by a margin, epsilon, some margin. And if it does beat the previous best model, you update. You say, congratulations, Jelani, you're now #1. And you know, if not, you say, sorry, you didn't improve, and I can't tell you your score, okay? So either you improved by a margin and I give you the score and say you're number one, or you didn't improve and I say you get nothing, okay? You know, I don't want to tell you what it is because you didn't improve. And so if you try to work with leaderboard error instead, so you're just trying to do this, you can get much better error bounds. Okay, so we found that like actually simple analysis of this algorithm recovers this logarithmic dependence on k. Okay, so you can go again back to like logarithmic dependence on k instead of this polynomial dependence on k. So that's an exponential improvement in k. The rate is a little bit off, and that's been bothering me since then. And nobody else solved this problem, so I tried to work on this myself, and I came up with this unfortunate exponent of 2/5. Okay, so and I think the worst or the most difficult part of this theorem was convincing myself that 2/5 is bigger than 1/3 and less than 1/2. Okay, and you know, every once in a while I wake up from a nightmare and I think I got it wrong. It's actually somewhere outside this interval, and you know. But I think it's between there somewhere, okay? But we still don't have the tight bound. Okay, but actually in this paper I also give some argument why this is probably the tight bound. So you get some kind of weird exponent and I don't quite know why, okay? So this is the leaderboard error, right? And one thing I find fascinating about the ladder algorithm is the following simple question. Is it prescriptive or descriptive, right? Is this an intervention or a natural algorithm? Is this something the community implements on its own, or is this something that you should implement? Okay, and I'll actually argue that it's both. Okay, so you could think of the ladder algorithm as like an intervention that you can implement in a benchmark or in a competition when you're really worried about overfitting, and then you get the strong guarantee on like limiting overfitting. So you can think of it as an intervention, but you can also think of it as a natural algorithm in the sense of Bernard Chazelle, remember the whole bird flocking stuff. So it's something that the community does on its own, okay? And you can say if you start from a postulate about the behavior of the community, you end up with an interesting outcome, okay? So it's a bit of a sociological argument. It's saying like, let's start with an assumption about the community, and then you actually can show that these benchmarks have more longevity than worst case bounds suggest, okay? And this is also like how I like to think about it. So the apparent like ignorance of the community or a sort of obsession with best possible results has some kind of positive outcome for the scientific well-being of the community. So I found that a little bit counterintuitive. Good. So, and then something amazing happened. Sometime in 2019, a team from Berkeley did the following. Ben Recht, Rebecca Roloff, Ludwig Schmidt, who's in the audience, and Vaishal Shankar decided to do the following interesting experiment. They created new test sets for CIFAR10 and ImageNet, two of the most well-studied image classification benchmarks. And they went back to like the original description of the data collection procedure, and with like painstaking effort, they tried to recreate new test sets for these old benchmarks. And then they reevaluated all the models that have been proposed over the years on these new test sets. Okay, that seems interesting. Okay, so what they found, and this is striking, is that the model ranking, like which model is better, like the performance of the models relative to each other, the model ranking that had been determined over the years, is preserved, okay? So the kind of plot they always get in these things is the following. At Berkeley, we call this the Ludwig scatter plot. And it looks like this. You have the old test accuracy on the x-axis and the new test accuracy on the y-axis. And every dot in the scatter plot is a model, okay? It shows you the performance of the model on the old and the new test set. And it always happens, for reasons that are not entirely clear, that these models cluster on a line, okay? And because this line has positive slope, you know that the better you were on the old test set, the better you are on the new test set, okay? You also see that performance drops, so the line is below the no change line. It drops because there is some distribution shift in the new test set, so the performance does go down. But I'm more interested in the slope of this line. So let's think about this. Okay, so and I'm going to convince you that this is actually evidence against adaptive overfitting on these benchmarks. So let's consider the Ludwig line. Let's look at the old accuracy versus the new accuracy. And let's just abstract out these models and let's say we have this line. And let's think about the slope of this line, okay? So positive slope means the following. Highest accuracy on the old data set is also highest accuracy on the new data set. So in other words, if your goal was to be best on the new data, the thing you should do is, hit the old data as hard as you can. Okay, so if you just like go as hard as you can on the old data, you're going to be the best on the new data. But it gets even more interesting if you go to slope greater than 1, and actually a lot of the times we see slope greater than 1, which means that the performance drop of newer models is actually less than the performance drop of previous models. Okay, so the newer the model, the higher the accuracy was, the less the accuracy drops when you go to the new test set. And that is striking because that really says, even though you had more time to adapt to the test set, you had more time to overfit, there were more adaptive evaluations against the test set, your performance actually drops less. So it seems like you actually overfit less to the test set than you thought, okay? And we were intrigued by this, and we evaluated this kind of thing, or we did the scatter plot for all the Kaggle competitions, and I worked with Sarah Friedrich-Karl, John Miller, Ben Recht, Rebecca Roloff, Ludwig Schmidt, and Vaishal Shankar. And we did this meta-analysis of more than 100 Kaggle competitions that have been done over the years, and we saw the same. Okay, we see the same kind of lines, and we see the same kind of lack of adaptive overfitting. And even MNIST, for crying out loud, the thing that you might think is the most overfit benchmark. It's been around for more than 2 decades. It's been like ridiculed to no end for being like a toy benchmark. Even here, there's a beautiful paper by Yadav and Botu called The Lost MNIST Digits, where they found some drawer with like extra MNIST digits, and they evaluated all the models on these like lost digits, and they get the Ludwig line, okay? And so, it's swapped here because they swapped the X and the Y axis, but it's the same thing. It's the same thing, okay? So even MNIST, which has seen so much activity. And so it's worth asking, what makes static benchmarks live so long, okay? Why is it that these like things that you put in the world and forget about for 2 decades seem to still work, okay? And so, 5 minutes. Yeah, if you ask me, I would have said, well, it's the ladder algorithm, right? It's the ladder postulate. It's because we're doing this leaderboard business, and that mitigates overfitting. But my collaborators at Berkeley wouldn't believe me about the leaderboard principle, and they wanted to have additional evidence. So we poked at this a little bit more, and we identified like 3 sort of principles that mitigate overfitting. And these are sociological and psychological factors, and not necessarily statistical arguments, okay? The first one's community dynamics, things like the leaderboard principle, but there's more here. The second one is the mind of the analyst, the way the analyst thinks, and that also mitigates overfitting. And the third is problem artifacts, okay? Things that you might overlook at first about the problem formulation actually have significant impacts on the amount of overfitting that you expect, okay? So one thing we can show is collaboration actually mitigates overfitting. So this work with Horia Mania, John Miller, Ben Recht, and Ludwig Schmidt. We can, again, start to make some kind of postulate about the community. We could say scientists have shared priors and practices. Machine learning practitioners try out similar things. And what we see empirically is, in fact, this seems to be true. A lot of the ImageNet models that have been proposed have high agreement in their predictions. So let's say you have 2 80% accuracy models. If predictions or errors were random, they would agree in 68% of the positions, right? But you see actually much higher agreement in the predictions. And so we can turn that high rate of agreement into better generalization bounds. Okay, so if you have similar models, you get better generalization bounds. So trying out similar things mitigates overfitting. Second, one thing we did is we looked at the individual analyst, and we thought, well, what is actually going on in the mind of the analyst? And we're trying to come up with something that's not a worst case analyst, but like, what is a natural analyst? What does it mean for an analyst to not behave adversarially? Okay. And in work with Tiana Zernick, we came up with a dynamical systems view of the analyst, where we model the analyst as a dynamical system that takes in a result from the holdout set and spits out a new query, spits out a new model. Okay. And then you get this nice correspondence between control theoretic constraints on the dynamical system and cognitive limitations of the analyst. For instance, the stability of the system corresponds to a recency bias of the analyst, whereby the analyst weights recent information more strongly, and some kind of Lipschitz condition on the system has the opposite effect. It would lead to some kind of anchoring bias, whereby you sort of ground your initial or you ground your analysis in initial findings, and you try to sort of confirm them, okay? So this is one view of it, but there is another thing, and this is these, okay, yeah, if you do this again, you get some kind of, error bounds that scale between the adaptive case, a non-adaptive case and the adaptive case, and depending on how strong the cognitive bottleneck is, you're either in the fully non-adaptive case or in the fully adaptive case. So it's some kind of way of going beyond the worst case and arguing why sometimes we don't get these worst case bounds. The third principle I want to highlight is problem artifacts. I don't know if you know this, but like ImageNet has 1,000 classes. And of these 1,000 classes, I think 30 are terriers, okay? And I think no human being has any right to know more than 3 kinds of terriers, okay? And I don't even know there should be that many, but apparently there are 30 kinds of terriers. And so there are all these like seemingly like similar classes that are kind of hard to distinguish. And work with Vitaly Feldman and Roy Frostig, who are both in the audience, we showed that this kind of like multiplicity of classes actually mitigates data overuse. So we can often replace the dependence on the number of data points, n, by something like n times m, where m is the number of classes. So the number of classes blows up the effective data set size. But of course, you can't just go and copy your classes. You can't just copy your data set and then replace the class names. There's some assumption about the priors on these classes. You can look at that in the paper. So let me summarize and then wrap up. How many? 3 minutes? 2 minutes. Oh, three. Okay. 3 minutes. Okay. So you said 4. Okay, 4 minutes. So meta-analysis, and the benefit of hindsight revealed that adaptivity was actually more benign than worst case bound suggested. And we now have some theory to explain this outcome, but it isn't purely statistical. It's sort of like interestingly about the community and how it clocks, okay? And in particular, it's about, community dynamics, the mind of the analyst, and the problem formulation. And all of these things are, important for what we get, right? What comes out of this, okay? And so there are sort of 2 ways of looking at it. And I don't know where you landed, but I can tell you where I landed. So the first one is to say, great, this is wonderful news. It shows that static benchmarks have surprising longevity. Okay, so you could say, wonderful, we don't have to worry about it. These things just keep on living, right? But there's the other point of view, the flip side, and this is where I sort of come around to, is that if there is scientific harm to the way we use benchmarks in machine learning, then generalization gap doesn't pick up on it, okay? This kind of way of going about it with like measuring the generalization gap apparently doesn't show that there's anything wrong with these benchmarks, if there is, okay? And so maybe we should think a little bit further on like about benchmarks and where we expect things to go wrong if they do, okay? And so in fact, the benchmark debate is more active than ever. It hasn't gone away. And there's lots of concerns with static benchmarks all over the place. There are many papers now articulating them. I'll give you one example from Bowman and Dahl, 2 NLP experts, who wrote a very interesting paper called "What Will It Take to Fix Benchmarking in Natural Language Understanding?" And they reflect on many of the issues with static benchmarks, but also with newer proposals of benchmarks. And so there was a panel related to this at NeurIPS. If you want to learn more about that, I can recommend. And so one of the proposals that they talk about is what's called the dynamic benchmarks, a dynamic benchmark. And it's a proposal that's meant to replace static benchmarks. So instead of having a fixed data set, in a dynamic benchmark, you keep evolving a data set over time, and the data set changes with the kind of models that you propose. Okay, and there are already platforms like DynaBench implementing dynamic benchmarks. Okay, and so the way this works in a dynamic benchmark, you start from some data set, you let the model builders build some models, you let them compete, you take the best model that you found, and then you adversarially collect data so as to fool the best model that you found. And so you sort of trying to find hard cases for your current best model. And then you take this adversarially collected data and you throw it into your data set and you repeat, okay? And the idea is that you somehow grow a data set that keeps getting more and more challenging as your models get better. And you get the sort of everlasting, ever improving, dynamic interplay of model building and data collection. And so we wanted to know if this works. And there was disagreement among practitioners as to whether this works. And so in a recent work with Ali Shirali and Rediat Abebe, who are both in the audience, we proposed a theory of dynamic benchmarks, and it's very simple, actually. So a dynamic benchmarks is just a directed acyclic graph with 4 operations. The operations are model building, model assembling, data collection as an adversarial data collection, and data pooling. And you can stitch together any the benchmark you want from these 4 primitives. Okay. And so the standard design that I mentioned that's currently being implemented out there is just a directed path with alternating model building and data collection steps. But in principle, you could have anything you want there. And so what we're able to show is that actually in the standard design that people implement, progress can stall after just 3 rounds. So there's no reason to expect that things will progress beyond 3 rounds or a constant number of rounds. And we can get strictly more improvements with more complicated hierarchical designs. But these are also computationally more expensive. And so there's a trade-off between the complexity of the benchmark and how much progress it can guarantee. Okay, so with that, I'm going to wrap up, and I want to sort of attract your attention to sort of this broader perspective on scientific validity, and sort of reframing the debate to be about like what determines the health and validity of our scientific and epistemic activities, rather than just like, are we overfitting or what's the generalization gap? And there are many sort of components to this, right? So there's the traditional statistical measures like generalization gap, but there are these broader issues of problem formulation, mind of the analyst, or community dynamics that actually determine what scientific outcomes we can hope to expect. And so, yeah, I hope to get you sort of interested in studying some of these questions going forward. Thank you.
Hi, you said there was an improved holdout method based on differential privacy, but you didn't discuss it at all. Can you tell us something about it?
Yeah, I can tell you about it. So what's the improved holdout method based on differential privacy? The simplest thing you can do is basically you use noise addition. Whenever you report the empirical risk of a model, you report the empirical risk plus some noise variable, and you use differential privacy to analyze what that noise addition does. So yeah, it's easy to implement. It's just noisy. It's a noisy holdout method. So empirical risk plus noise. Oh, it's in any of these papers. The one I mentioned with it's called Preserving Statistical Validity and Adaptive Data Analysis. I'm happy to send it to you. But it's. I don't have references on my slides, but you'll find it if you search for statistical validity, differential privacy. They'll bring it up. Yeah.
So, Moritz,
it
seems that the ladder mechanism cannot explain a slope larger than 1 on the Ludwig line. So what is the evidence that this ladder is actually going on?
Yeah, so that's right. This is also why people gave me a hard time about it. So Boaz is saying the ladder algorithm can't explain a slope larger than 1. The ladder algorithm can't even explain, this drop, right? Because the ladder algorithm will bound like empirical risk and risk. So I think for starters, I would also like to have some theory which allows us to reason about the case where you keep making improvement, but it's not necessarily close to like the population, okay? So you keep getting better, but you still kind of diverge from the population. And so, yeah, the ladder algorithm, it's a little bit of a, I'm a believer, but, I have my arguments. It's not a full explanation for more than one reason. One is the one you mentioned. The other one's the disconnect between the distribution shift that's in the picture. Yeah.
Last.
Hey, so could you validate your hypotheses about the effects of the community by using them as anti-prescriptions and simply ignore all the community standards and scientific methods and try to adversarial win all the competitions?
Yeah. Yes, and we did. Okay, so there are many people who did these shenanigans of like climbing the leaderboard and like forcing large errors on these competitions. And yeah, it's feasible. It's just not what's happening. So it's interesting that you can really force it to happen if you try, but it doesn't happen on its own. Yeah.
Thank you, Moritz, for the insightful talk.
Thanks.
The final program for the day is a panel discussion